Okay, so just some last few odds and ends that we should probably discuss. Um, what do we do if the edge costs are not unique? Remember, we were assuming the edge costs were unique this entire lecture, but what should we do when the edge costs are not distinct? And really, we could just make the edge costs distinct by adding a small, tiny, and different cost to each edge. Okay, so really the only thing that happens when the edge costs are not distinct is that you could have more than one minimum spanning tree, right? So in that case, I mean, really you're just looking for a minimum spanning tree, right? I'm assuming that you're not looking for all possible minimum spanning trees. That I believe is a NP-hard problem. So assuming you just want to find a possible minimum spanning tree, just add a point 0.0000001 addition to the edge weight, or 0.0000002 edge weight. That should take care of it. It'll still give you a minimum spanning tree. Okay. What about if the edge costs, we assumed all the edge costs are positive. What happens if they're positive and negative? Okay. And here's the important thing. All the algorithms and proofs that we made so far don't assume that the edge costs are positive. Okay? So, really, all the algorithms we considered would be able to handle negative cost edges very easily, naturally, right? Or, I mean, the other option is that you could just you could just modify the graph and just add a constant threshold, a constant value to all the edges and make them all positive. Now the question you're going to say is, but wait, in the 2 lectures ago, in the shortest path lecture, you said that you can't reweight the graph by adding a constant value and making all the edges positive. And that's true. That's true. In the shortest path graph, I said that you couldn't do that because you would penalize paths that take more edges over paths that take less edges. But in this case, when we compute the minimum spanning tree, we're not computing the path. A path composed, we're not comparing different paths that are composed of multiple edges. We're just computing literally edges. We just have, is one edge bigger or smaller than the other? So when we're computing the minimum spanning tree, the difference is that we're comparing literal edges. So if we renormalize edges, none of our comparisons become any different. Okay, in but in the case of shortest paths, if we're comparing the lengths of paths, and because we're comparing the lengths of paths, renormalization like that doesn't work. Okay.